When an external voltage is applied across the diode such that N side is positive and P side is negative, it is said to be reverse biased. The applied voltage mostly drop across depletion region. The direction of voltage is same as the direction of barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in electric field. The effective barrier height under reverse bias is V0 plus V. This suppresses the flow of electron from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the diode forward bias. The electric field junction is such that if the electron on P side and holes on N side in their random motion come close to the junction, they will be swept to its majority zone. This drift of current gives rise to drift current. The drift current is of the order of a few microampere. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also there under forward bias, but it is negligible microampere when compared with the current due to injected carriers, which is usually in milliampere. The diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to sweep the minority carriers from one side of the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage, but is limited due to the concentration of the minority carrier on either side of the junction. The current under reverse bias is essentially voltage independent up to critical reverse bias voltage breakdown, known as breakdown voltage. When V is equal to VBR, if the current is not limited by an external circuit below the rated value, the PN junction will get destroyed. Once it exceeds the rated value, the diode get destroyed due to overheating. This can happen even if the diode under forward bias, if the forward current exceeds the rated value. The circuit arrangement for studying the VI characteristics of a diode, that is the variation of current as a function of applied voltage. The battery is connected to the diode through a potentiometer or rheostat so that the applied voltage of the diode can be changed. For different values of voltage, the value of the current is noted. A graph between V and I is obtained. Note that the forward bias measurement, we use a milliammeter since we expected current is large. While a micrometer is used, ammeter is used in reverse bias to measure the current. The forward bias, the current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After the characteristic voltage, diode current increases significantly even for a small voltage in the diode bias voltage. This voltage is called the threshold voltage or cut-in voltage. For the diode in reverse bias, the current is very small and remains constant with change in bias. It is called a reverse saturation current. However, for special cases at very high reverse bias breakdown voltage, the current suddenly increases. This special action of the diode is used in special purpose diodes, which is used and specifically speaking in Zener diodes. The PN junction diode primarily allows the flow of current only in one direction, forward bias. The forward bias resistance is low as compared to the reverse bias resistance. This property is used for rectification of AC voltage. A quantity called dynamic resistance as the ratio of small change in voltage delta V to a small change in current delta I. RD is equal to delta V by delta I.